At this point, we've covered how the tests for each fault are generated, and the role that scan plays in making that happen. The next step is to compact all these individual tests into a smaller number of test patterns. Tests for single faults may be merged if they do not have conflicting values applied to the same primary input, and if the launch and capture clock and control sequence is the same. The scan sequence is always the same, by construction. The compaction program maintains buckets of patterns with compatible clocking, and keeps track of how often a new test is merged into a particular pattern. Based on user-selectable criteria, the program will decide when it appears that no more tests are merging into a pattern. The remaining unspecified bits of the scan load are filled, usually with random data. The pattern is then passed to the fault simulator. In the fault simulator, the good machine response, no faults applied, is compared to the response of the circuit, with each untested fault applied, one at a time. When the responses differ, the fault is marked as detected. During the process of generating ATPG patterns, there are usually a number of scan bits that are not specified to a particular value. These bits usually are randomly filled to get fault coverage through serendipity. Instead of random fill, Modus has an option to do constant fill or repeat fill. Constant fill places the same value in all unspecified bits. Repeat fill option uses the last care bit to identify which value to repeat. Both of these can help reduce down switching and might help in power reduction, but might increase pattern count because less faults are being randomly tested. For an average pattern of a large chip, the density of the specified bits will be less than 2%. There will be a few patterns in the set that have specified bit densities in the 20% to 90% range, and many that have densities well below 1%. The first few patterns will have very high density and test many faults. Here we show the values to be loaded for a single pattern into 3 scan chains in a chip that is being tested. The test generator creates a test for fault 1 with just a few bits specified, and this is passed to the compaction program. Perhaps this is the first test cube, as tests for single faults are called. Let's say this test cube doesn't fit in any existing vector, so the compactions program creates a new vector that initially contains just this one test cube. Tests for additional faults specify additional bits as they are merged. Note that the different tests may share some specified bits. Here you can see that fault 2 and fault 3 are sharing the specified bits. After some time, with no additional tests merging into this pattern, it will be filled and sent to the fault simulator. Note that most of the data that will be scanned into the chip is fill, usually pseudo-random data. This low density of specified bits has 2 important consequences. Most of the test data is fill, and many of the faults that will be detected in the fault simulator will be detected by this fill data, especially pseudo-random fill. This happens because the fill accidentally sensitizes and propagates a fault effect. The low density of specified bits allows us to compress the test patterns. The patterns will be decompressed and filled by on-chip logic. Compression is actually performed as part of the compaction of the individual tests, and details are covered elsewhere. However, compressed test patterns may have average specified bit densities in the 20% to 80% range, instead of the 1% to 2% range.